that stuff from linear algebra, but there's not a lot of results in that direction as far as I know. So for this reason, people have introduced what are called Hermitian adjacency matrices. And I say adjacency matrices because you can create your own Hermitian adjacency matrices. What do I mean by that? So for directed graphs, if you have something like this, like x arrow to y, and maybe you don't have the other way around, you don't have the arrow from y to x, how do you capture that in a matrix? So in this matrix, you can put axy to be some complex number, and in the position yx, you can put the conjugate of it. Which complex number to put? That's where you will see adjacency matrices. So there are, initially people put here I, and you put here minus I, and then people put cube roots of unity, and then obviously the other, the conjugate of it, and then now people are putting 6 roots of unity here, and so on. So there's a variety of adjacency matrices that you can define. Again, it may seem complicated. Why do you do this Hermitian? Well, Hermitian is to capture this. As we mentioned at the beginning of the lectures, it has a spectral decomposition theorem, and it has real eigenvalues. So you will get a lot of. I don't know if you realize, but pretty much almost all the results that we proved this week, you had this basis of orthonormal eigenvectors, and it helped you in many ways. Okay, so that's the same thing here. So if you're interested, look there. Now here, there are various approaches. Some people study like higher dimensional arrays. Like if instead of looking at the at the matrix, which is kind of like a 2-dimensional thing, you can look. If you have a hypergraph, I mean, for those of you that don't know, in a hypergraph you may have like things like triples in an edge. Okay, not just pairs. So how do you capture this kind of interaction by more than 2 things? So you can define higher dimensional arrays, and try to say something. There is work there. Or also you can define you can regard the hypergraphs as simplicial complexes. And look at higher dimensional Laplacians and adjacency matrices. So let's say you have a 3 uniform hypergraph. So this here you can follow the work here just by keeping in mind that what happens for graphs. A graph is a kind of one-dimensional simplicial complex. So what happens for graphs? You saw in the presentation by Professor Karan, you have the Laplacian. The Laplacian arises from this incidence matrix between vertex versus edge. That's how you get the Laplacian. So something similar will happen here. So let's say you have something that is in which you have triples and so on. What you can do is you can try to see how pairs of vertices interact with your hyper edges. So you can have like similarly like incidence matrices here, and from these incidence matrices you can make Laplacians and you can study their properties. Okay, it is more. I mean, there's recent work in this direction, so I'll be happy to give you some references if you're interested. Just send me an email, okay, for both of these things. But these are kind of the directions where it moves away from undirected graphs and moves into this direction. Of course, there are other directions that I haven't covered here. There are directions in which, like, some people have done this recent interesting research on how you put weights. You can put weights on the edges of a graph such that certain properties are satisfied. So there's work in that direction. but I haven't, I didn't have time to cover it and it's not fair to you to give you so much material for such a short time. So I'll keep this short. I hope you learned some things this week, and I hope this will keep you motivated to learn more, and hopefully you will find your interest in this area to be greater after this week than it was before. Like I said, I'll be happy to answer any questions that you have. You go home, do your work, write things down, and then if you have questions, send me an email, and I'll be happy to answer any questions that you have. I'll keep it short this time. I just want to thank you for being so patient for a whole week. If I were in your place, I wouldn't have been able to sit for listening to myself for so many hours. So I just want to say I'm very grateful, and I'm very happy to have met all of you, and I hope we continue to stay in touch. So thank you very much. I'll stop here. Thank you. So we'll keep it short. Yeah.
I asked me if we solve.
We have another 40 minutes. We have to do something. Okay. Okay, maybe we mentioned one topic in the syllabus, cospectral graphs. I will say something about the cospectral graphs and the graphs determined by set. Sorry?
One general thing could be,
Yes.
I've never seen take a spectrum, you know only the spectrum, and you somehow arrive at some graph. I've never seen such a thing. So just
That's the inverse eigenvalue problem. Yeah.
how do they do it? If you can comment on this.
Okay, so I think Sebi can comment that about
This is the cospectral sum. Yeah.
He's just talking about graphs determined by the spectrum.
Yeah.
Okay.
Not just determined.
Give me a set of real numbers which adds up to 0.
Oh, okay. That's harder. But let's listen to Professor Karan and
Okay,
yours.
yeah. So given a graph, you can associate a matrix. We'll deal with only adjacency matrix. So you can find out its spectrum. So spectrum of A of G is an set consists of n numbers. Okay. Now the question is whether if I give you a graph on n vertices, I know what is its spectrum. Whether this is the only graph which assumes this is a spectrum, or can you construct some other graphs for which this set will be a spectrum for that. Okay, this is an interesting problem which considered in I think 56 and some 1950s. So first people thought that like isomorphism and the cospectral are the same. Okay, if two graphs are isomorphic, if and only if their corresponding adjacency spectrum are the same, but quickly people realized that that's not true. Okay, so let's start with a simple example. I'll focus only on adjacency matrices. I'm not going to discuss Laplacian. Okay, so you take a graph on 5 vertices in this way. So this is 1, 2, 3, 4, 5. You take these two graphs. Okay, this is my G, this is my H. So now you are enough training on calculating the spectrum or computing the spectrum. Now you should be able to tell me what's the spectrum of this graph. Huh? So for A of G, what is the spectrum? Okay, so this is 0 with multiplicity 3 and 2 and minus 2 with the multiplicity 1. What about spectrum of H? Okay, so what is the argument for here? What is the argument? Why it should have 2 and minus 2 as an eigenvalue? So it has a component which is bipartite, complete bipartite. For complete bipartite, you know all the eigenvalues. Okay, so square root of plus minus square root of PQ. So here P equal to Q equal to 2, hence you are getting 2 and minus 2. For the second one, it's star again complete bipartite, 1 comma 4, K 1 comma 4, hence you have the spectrum as 2 with the multiplicity 1, so minus, okay, 2 with the multiplicity 1, 0 with the multiplicity 3, and minus 2 with the multiplicity Okay, so clearly these two graphs are not isomorphic, right? So I think Amos used to call this a Saltaire pair. So because his argument was you just superimpose this graph H on G, and you're going to get a flag that is, I think, Scottish flag. So that's known as Saltaire pair, Saltaire flag. So I think he calls this as Saltaire pair. Okay. Okay. So so in this type of situation, we say two graphs G and H are cospectral if they share the same spectrum. Spectrum of A of G, this is equal to spectrum of A of H. Okay. So we say a graph is determined by spectrum. Okay. So G is determined by its spectrum if the following happens. Whenever the adjacency spectrum of G is same as the spectrum of adjacency matrix of some other graph H, this should imply G is isomorphic to H. Okay. So in short, we will call this type of graphs as DS graphs. Okay, graphs determined by their spectrum. Then what is NDS? The graphs which are not determined by their spectrum. Okay. So NDS is same as not DS. Now the question is like, what are the graphs which are determined by the spectrum? What are the graphs which are not determined by the spectrum? Okay. Already we have seen one example. Kane, if you remember, the complete graph on n vertices. Okay. What is A of Kane? J minus I. You know the entire spectrum. The eigenvalues are n minus 1 with the multiplicity 1. And minus 1 with the multiplicity n minus 1. Okay. So if any other graph on n vertices, if it assumes this is a spectrum, then the graph should be isomorphic to Kn. Okay. The argument is simple. If you know, otherwise, how many of you don't know this this fact? Kn is determined with spectrum.
I know because we saw it.
Okay, you don't know. Can you think for a minute? Can you give some idea how to proceed? The question is like you start with a graph which you don't know a priori what it is, but you know its spectrum. Spectrum is n minus 1 with the multiplicity 1 minus 1 for minus 1 with the multiplicity n minus 1. Now I want to show that any such graph should be isomorphic to complete or the complete graph. Okay. Can you think? I'll stand here.
The relationship between max degree and oh, that's max degree.
Yes.
Means if I remove A means lambda and 62 minus 1, it means rank is 1, which means all the process scalar multiple of 1.
Rank of which matrix?
A plus adjacency.
A plus adjacency matrix.
Plus
Okay.
A plus identity.
Okay. A plus identity you mean? Okay. The spectrum will get shifted. Okay. Rank 1. Okay.
Rank 1 means 1 plus 1 holds scalar multiple of 1.
Yes. Yes.
And adjacency matrix only 0 or something.
Yes.
Which means everything scalar, like the scalar is 1 each.
1. Yeah. Fantastic. Yeah. Yeah.
Only that can have that is.
Okay. Okay. Good. Yeah. So the one argument what friend says is, so A plus I has, so spectrum of the eigenvalues of A plus I or A of kn plus I. What are the eigenvalues? We have to add 1 to it. Okay, so n with the multiplicity 1 and 0 with the multiplicity n minus 1. Okay. Wait. A of g. I have to start with some arbitrary matrix, arbitrary graph. I have to show that is isomorphic to Kn. Okay. So this is rank of this matrix. Rank of A of g plus I is equal to 1. Then what can you say about A? Every row of the matrix A should be a linear multiple of one of its rows. Okay. So can you say one row? All the entries are either 0 or 1. Okay. It should be of the form something like we know only it is every row is a linear multiple of one of its rows. But there should be AG. AG plus I, right. Yeah, very good. Diagonals are 1. That forces that all the entries should be equal to 1. Because the natural question is some zeros may be there. How to overcome of the 0? Because diagonals are equal to 1. So I'm going to get everywhere. So that means that A of g is equal to j minus I. That is same as saying that the graph is Kn. Very good. Yes.
This doesn't require the other n minus 1 eigenvalues. We are determining it by knowing the fact that n eigenvalues are n minus 1 of them are minus 1.
Yes.
That is necessary to. It's a sufficient to get that it's a complete graph. You do not need a full spectral information. You just need the information that there are n eigenvalues.
Okay.
And the n minus 1 of them are minus 1.
Yes.
That would determine it's a complete graph.
How does it trace the other eigenvalue has to be n minus 1?
No, I think there is a characterization. I think the graph has n minus 1 negative eigenvalues if and only if.
Yeah, but here you want to do it just with your bare hand, not with using anything else. Just because you're done. Like what else are you?
No, what he's saying, I know only minus 1. Your argument is right. Oh, if you say minus 1 with multiplicity n minus 1, whatever he said, that will work. Yeah. So, is it clear what he said? If you are keeping minus 1 as an eigenvalue with the multiplicity n minus 1, since the trace of the matrix is equal to 0, the left out eigenvalue should be equal to n minus 1. Yes, that is right. Yeah. So that leads to another question, that is if you have n minus 1 negative eigenvalues, then it should be complete multipartite graph or complete graph itself? Complete multipartite graph. Yeah, that's one characteristic. Okay, so what are the other graphs? Can you give me one more graph which is determined by spectrum? Path graph. Okay, if you say path graph, you have to prove. Okay, we will prove together.
Calculate the eigenvalue.
Yeah, first thing is you have to calculate eigenvalues of path graph. Any one of you tried that? How did you get the eigenvalues of path graph? Cycle you want to do? For path or for cycle?
This come, that will come, we can write that.
Different formula, like Fourier.
From cycle it will come.
Oh, you want to use the formula and then say?
So one direction is easy, but the other direction, at least in spectrophobic, it's like investigation.
Yeah, come. Okay.
Say why I'm not coming.
Ha ha ha.
One direction is easy.
Hmm.
The other direction, if the spectrum is defined.
Okay, whatever direction you know, you comment, right? The others will help.
The other thing,
Uh-huh.
at least in the book, he described spectrophobic, he explained is that this is there, this is not there. Like the investigation basis, it goes. That's it.
Okay, anybody else who suggested path graph? Come.
Come to the.
Come.
We asked you to come.
Come. You know, right? Comment, right? Anyone? You want to come? Come. Where is Debrata? You can come. You know, right? Come. I don't. A of Pn.
So what is the question?
Path graph is written by which spectrum? A of Pn.
Okay.
Write down. Okay. What is the spectrum?
So, okay, the spectrum, you can remember it is 2 times of cos, then k,
Pi by.
10 plus 1, 2. This will come using the eigenvectors. First we know the eigenvalues of Cn. Cn are the eigenvalues. Then using an eigenvector of path, just you can.
N or n minus 1?
It is.
Either one or.
Okay. Yes. So this is the eigenvalue. And we know that it's a tridiagonal matrix. Shall I explain the eigenvalues, how to find the eigenvalues of this? Or?
Yes.
Fine. Well, write ACN as matrix Q plus Q transpose, where Q is this. One. And if we multiply Q, it will be Q transpose. Because if you just multiply Q square, so this diagonal will just shift by 1.
Q inverse equal to Q transpose.
Yeah, Q per and also identical. Right? On this. So this is Q plus for n minus 1. So we know the eigenvalues of this matrix because its characteristic polynomial is x for n is equal to 1 or minus 1 is equal to 0. So the 1th root of unity, right? And we know that this q and q power n minus 1 has the same eigenvectors. If we have the eigenvector of q, then we know the same eigenvector, so we can calculate it. We'll get these eigenvalues. After that, how this out from APN will go to C of 2n plus 2. I'll write C of 2n plus 2.
You want to? I have the book. I can give it to you.
Yes, sir.
You can use it. Next page. Here.
Take this two eigenvectors. This will be the linearly independent eigenvector. And as I told, like if you just carefully do the partition of this adjacency matrix of ACN, it will somehow so this will give two independent eigenvalues. The same eigenvalue will like act as an eigenvector corresponding to the same eigenvalue. Yes. So we know that the eigenvalues of C2n plus 2. What are those? What are the eigenvalues of this C2n plus 2? Sorry. We can start with 1 to 2n. So this will give us so up to n, if you just take n plus 1, then n plus 2, that will like how can we use twice for this? This cosines will follow that will like it will again coming with the same. So this will make that these are the eigenvalues for the path. I can take an example with T10, like, but I think
Right,
this is the
fine.
like idea, like because just making this C2n plus 2 as union of Pn and Pn, then to vertices, and by just carefully choosing this eigenvector, you can like take that these are two eigenvectors of this matrix S with C2m plus 2. So then you can calculate. But I think there are some other also techniques. Like we know that this Pn has this, if we write the characteristic polynomial of Pnx, try to write that polynomial, can be written as so it is somehow follow the Chebyshev polynomial, like the second kind of Chebyshev polynomial, and there are very like nice notation for that, and we know the roots of the Chebyshev polynomial of second kind. So this polynomial will satisfy somehow. Just you have to just change the this x will be somehow I think changed by 2y or something. Then using that also you can find the eigenvalues. It will follow some polynomial like. Yeah, I cannot recall that.
Yeah, that's fine.
But that's also can be done.
Good, thank you. Okay, then who wants to show path is determined with spectrum? Come. That's the spirit, come. You can erase this. But we can use that.
So we know the adjacency spectrum of the path graph, and it is 2 cos ik divided by n plus 1. So one can easily see that its Laplacian spectral its spectral radius is less than 2. Okay. So now first we will prove that the graph G that is going to be have the same spectrum with Tn need to be tree, need to be a tree. Okay. So
Wait, so those who are seeing it for first time, why if a graph is cospectral to Pn, why it should be a tree?
I am going to prove this.
You are going to prove it, okay, prove it.
So if G the graph, let's say G the graph, so we know that any tree on n vertices has n minus 1 number of edges. Okay. So if
We
G,
don't know the graph, right? We have only these two cos.
we know that this is a for the path graph, this is the spectrum. Okay. So we want to prove that the path graph is the only graph which has this spectrum. Okay.
This is his claim. He is not assuming. He is going to prove it is acyclic and connected. Both the things he will prove. Show first.
So if G is not a tree, then it is going to be disconnected. Okay, or it is going to have a cycle. Okay. So if G has a cycle, then it's induced a graph. If G has a cycle, let's say of order n, then we know the spectral radius of Cm, like cycle graph, that is equals to 2. Okay, so if G has a cycle of order let's say m, then spectral radius will be 2. Now we can use interlacing theorem. Then the spectral radius of Cm is going to be less than or equal to spectral radius of G, which is equal to 2. Okay. So G cannot have a cycle. So what is the graph that has no cycle and it has n vertices and with n minus vertices, so edges. What are the class of those graphs? So it needs to be a tree. Okay. So I have proved that it cannot have a cycle. G cannot have a cycle. So means that G must be a tree.
Yeah, but you need to show it has n minus 1 edges. How to show? Do you know any spectral formula for number of edges in a graph?
Radius of A square equals to 2 times number of B. Okay.
Look at the diagonal entries of A square. So we have seen that if you consider the power of the adjacency matrix, A power L, if you consider, the ijth entry gives you number of walks of length L between the vertices I and j. So A square, if you consider the diagonal entries, the number of walks of length 2 from the vertex to itself, that is nothing but the number of edges. Okay. So diagonal entries of the adjacency matrix gives you the degrees, sum them 2 times m you will get. Okay. So if two graphs are having same spectrum, then they should have same number of edges. Okay. So that fact if you use, then G is a tree. Yeah.
So G must be a tree. Now we want to show that that tree must be a path graph. Okay.
Yes.
So first thing I am going to show that if G means I am considering it as T. Okay. If this tree has star graph of order 5 as an induced subgraph, then we know that the spectral radius of S5 is 2. Okay, spectral radius of S5 is 2, which is,
You can draw the graph. I think terminology maybe people. K1, 4 he means. Okay. By S5 is K1, 4.
S5 means we know this spectral radius and it is equals to 2. So again we can say that the tree must not have a S5 as in this subgraph. So what is the structure? What structure will be left? Okay, so a vertex cannot have a, so there cannot be a vertex with degree 4. Okay. So now it might have a vertex with degree 3. Okay, so if we consider this graph, double side snake, I think. So this is one graph. So this graph has vertex with degree 3 and no vertex of degree 4. So there is one thing. Okay, if we consider, so it's, if we consider this as vertex set, so eigenvector as 1, 1, 2, 2, 2, and 1. Okay, then this will give the spectral radius as 2. This, if we consider this as an eigenvector, like A, B1, B2, B3, and up to so on. 1, 2. This vector will give as a spectral will give a spectral radius as 2 for this graph. Okay, so a graph cannot, so a tree cannot have a vertex, 2 vertex of degree 3. Okay, if this is an induced subgraph of T. So now what is left with us? We can have at most one vertex of degree 3.
Sorry? Connectedness. So he already shown that the graph does not contain any cycle, and the spectral, this lambda 1 square, the number of edges should be the same. So G is a graph on n vertices with n minus 1 edges. Sorry?
Take K2 union as 4 vertex and 2 edges.
Okay.
Okay, so this kind of induced subgraph we can have. So for this graph, as much as I remember, we need to calculate the number of box of length 4, and there the contradiction is coming.
Okay.
So for the path graph, so we know that, so this kind of graph will be there, okay? So trace of a to the power 4 of any graph gives us the number of box of length 4 from, let's say, I2. So for this, like if we consider it for some example, so we know that if they have, these two graphs have the same spectrum, that means they must have the number of box of length, they must have the same number of box of length from same vertex to same vertex. I consider it as I. So for, if I consider this as one graph and this as 3 to 5, 3 to 5. Okay. So these two have no, these two have not, do not have the same number of box of length 4. Let's say if I can if I consider the number of box of length 4 from 1 to 1, here and here, these two don't have the same number of box of length 4. So this graph is also eliminated. Therefore, the path graph is the only graph with this spectrum.
We can explain this last part one more time.
Okay, this part. Okay, so we so here what I'm doing, look, we have at most one vertex of degree 3. Okay, because if we have two vertex of degree 2, degree 4 or degree 3, then it will be eliminated from here. So this kind of graph is going to be there. If we calculate the number of box of length 4 here, and for this graph, these two are not same, because, and these two have to be same because they have the same spectrum. Trace of a to the power 4 means something like this must be there. But these two graphs don't have the same number of box of length 4. Okay. So first we have shown that this must be a tree, and from tree we have eliminated that it must not have a vertex of degree 4, and then from there we eliminated it cannot have a two vertex of degree 3, and here we eliminated it cannot have a vertex of degree 3. So it must be a path graph.
Okay, good. Neat presentation. Good. Okay. Any other volunteer with a question? Okay, complete bipartite graph, are they determined with the spectrum? Complete bipartite graph. Okay, this is on the board, okay? It need not be. Need not be. Yeah. It's K14.
If you could select it.
K44, K28.
K28. Just to play with the factorization. Yeah, this example is disconnected. So in general, like you can take, as he said, K44. Okay. Any other thing? You want to say something?
So that it's the same idea but a different proof. You define a matrix -1 for distance minus distance by j.
Okay.
To try to prove in a different way.
Okay. Block matrix you were saying.
Block? No.
Inductive.
That's different.
Okay. You write it and you will see. Okay. There is no other question. We can stop here. Want to discuss further? Okay, then we'll stop here. Yeah.